Good afternoon. This is kind of a blustery day, and John in particular, since you watch the videos from California, I'm sure the weather you have is much, much different. No snow closures today, but we've had snow squalls the past 2 days, and it's very windy out, and the wind chill is down to, I think, about 1 degree or something like that.
It's like negative.
Yeah, it's really intense. I mean, I have giant mittens that I wear, just because I've used those when I've gone skiing. But my big fat mittens, I like them. They look really big, huge, but my hands stay warm inside of them, and that's really what matters to me. So, and that's what I'll be wearing when I leave to walk back. Today we're going to, I wanted to have a vote on the exam date, but we'll have a discussion on it. We're going to transition into Chapter 3. We're going to get into modulation theory. There's a lot of fun things that lie ahead just around the corner, so I want to get into that. But the first thing I want to do is just, because we had the snow day, just to refresh ourselves on the calendar, I'm not having anything due this week. The homework is due next Tuesday. I might decide to give another mock quiz on Thursday, just another practice problem type thing.
We should do that. That was good.
Okay. Okay. I don't have a problem with it. I mean, I have them, that's the thing. So, and this has not been unusual to have something like this happen with the weather. So I put this up here just so you could see that these are the dates I'm proposing. So I'm proposing, just so you can see the week, that's the second week in March, so it's the 10th through the 12th. Whether or not I can have all your homeworks back, I don't know. I can definitely have quizzes back if I decide to give a quiz next week, which I think I will do. Just I have to play it day by day. I've been spending a lot of time on the search committee, and now we're finally scheduling candidates for interviews on campus. So I don't have lack of proof that my time has been spent on something that's producing. So to me, that's the most important thing. So of these new problems, though, they're all from the new chapter, and they get into actually the Hilbert transform, that number 7, which we may or may not get to that point next Tuesday. We'll just see how that shapes out. 6 and 7 are from the Hilbert transform, though. The very first problem, though, is a remainder of what we're going to talk about today with realizable filters. And reminds me, I have an article that I put somewhere on some computing device that was pretty interesting, but I'll tell you about it if I didn't put it on this computer. But at any rate, the first problem is just analysis of realizable filters, polynomial ratios of polynomials. So jumping back over to where we were at, over here in the end of Chapter 2, we were talking about harmonic distortion and intermod distortion. I looked over the papers to some extent, because not everybody even turned it in, but I think you've gotten the idea of what that is all about, and I gave you the tools to use for that, so that was good. Seems like I skipped over that example, and we talked a fair amount about group delay, but the homework problem, the very first one on set number 5, involves using this definition. So you have to take some derivatives, and when you think about polynomials in the S domain, and then you think about how you get the phase of a system function, you end up using arctangents, right? When you root a polynomial into its roots, then each individual root contributes one component into an arctangent. So you get an arctangent in the denominator, angles, and those are minus the arctangents for the angle, and then you have from the numerators. So when you're taking derivatives on that very first problem to get a theoretical expression for group delay, you're going to be taking the derivative of those terms with respect to f, and that will just involve using the integral tables. And I think one of the homework problems that was just put up the solutions for last week, because I'm just pointing out that if you haven't noticed back in the appendices, which is Appendix F in the book, there's indefinite integrals and definite integrals. And these are not your ordinary thick integral tables where you have everything in the world. The integrals that the authors have put in this section of the book are ones that tend to show up more frequently in the types of problems for this class. So they're kind of helpful to look there if you want to actually see it in black and white rather than searching on the internet for something. So I find it useful. I mean, I just count on it being there. And I know that I don't have to wade through a lot of stuff because they're kind of focused at what's needed. And my policy is if I ever give you a problem that requires some special integration formula, I will give you a page or give you a few examples. I won't necessarily give you the one integral that you need to work the problem. I might give you several, and then you have to figure out on your own which is the one that you need. But I will be sure to give you one that's one of them that's useful for working a problem. Most of the time, though, these sorts of things, you use tools to get it, like what I've got in Scikit DSP-Com for getting group delay, which is a numerical derivative idea. So this example, just briefly to comment on it, because I minored in electromagnetics and microwave circuits and that type of stuff, I always like transmission line problems, and because that way of thinking is pretty important in comms systems as well. So I have this as an example of a distortionless system.
Oh yeah, I was just doing the math for that.
In your other class though, right?
Yeah, ENM1.
Yeah. I taught that a couple of years ago. So for Dr. Song when she was on sabbatical, and if you want to see my Python stuff on this, it's on the website. It's on my website underneath that class. It's there. It's cool. And I also used LT Spice, and I had a microwave amplifier design project in the class too that was kind of an extension using S parameters. So if you can believe it, it all fits in. It fits in really well, actually. Transconductance of the device, it's S parameters from a behavior level model, and then building matching circuits, which is what you learn about in the EM1 class, right? Stub matching using Smith charts.
But only not dynamically, just a static frequency.
Yeah, that's no fun. You got to see what it does over frequency and see how it's got a passband shape to it.
Well, I will take ENM too, so.
No, you can do that, but LT Spice works for that. ADS
Oh, just
is,
spectrum analysis.
well, now the swept measurement type stuff in a simulator.
Yeah, the FRA.
You said FRA?
Frequency response analysis.
Oh, okay, that's what you call it.
Yeah, well, it's the acronym.
Okay. When you say FR in microwaves, I think FR4, the material,
Oh,
the epoxy fiberglass laminate that's used for printed circuit boards. But at any rate, what a transmission line is, it's a guided wave structure, and if you model it as a lossless structure and you have it terminated properly with the characteristic impedances, it forms this very simple input-output relationship. What comes out is what goes in, only delayed. So that's just simply the 1/2 is because of the effective voltage divider that's formed by the source resistance and the load resistance, and then the propagation delay is just comes from the length of the line divided by the velocity of propagation. The velocity of propagation is slowed down by 1 over the square root of the relative permittivity of the material, epsilon r, or epsilon effective, whatever it happens to be. Coax cables are homogeneous, so they're just epsilon, square root of epsilon r, whereas if it's microstrip, some transmission line that's a hybrid of air and some material, then it's a different factor. And I know that's in the class too, right?
I've got that part.
Yeah. That was all part of the stuff that I had them do. I actually had them lay out a filter and then build a low-pass filter with sections of transmission line and actually lay it out to physically see what it would look like. But the fact of the matter is, a real transmission line does have losses, and those introduce dispersion. So not all frequencies get the same attenuation, because the materials, there's both materials that make up a transmission line are lossy. The conductors are not perfect. They're not, zero conductance materials, copper, for example, and the dielectric, although it seems like a really nice insulator, it still has a loss tangent associated with it, which means it's lossy as well. So both of those things contribute to dispersion. So the line has a frequency response, and in LT Spice you can model those types too. Not as sophisticated as what you can do in our microwave design package that we use from Keysight, the Advanced Design System, or ADS, but so it still suffers from dispersion. I got interested in that a long time ago in my career because I worked in laser comm. I think I've told you that. But after I worked in the free space laser communications, I also got to work on an internal research and development project on wideband fiber optic. This was a long time ago, so it was only 1 gigabit per second. But I got to play with fiber optics and laser diodes and avalanche photodiode detectors, and that was kind of a fun thing. So I was really interested in the properties of fibers, and fiber, a big spool of fiber, much bigger than the one that I brought in. Remember the little one, the one that I had in my lab where I did my experiments was 1 kilometer long, but it was on a big, huge spool. It was just a big thing, big spool, and it was sheathed up to look like coax cable, and that I did my experiments with that. And I guess if you get into an industry job where you get to do some IR&D, go for it, because it's a lot of fun. You're getting paid to do something that's just a giant science experiment, and that's less pressure than being on a project where you have to make deliveries to the customer on a regular basis. This was just internal funding. Okay, just to understand the concepts of distortion systems, what was talked about up here, and I think I was kind of in a hurry when I was racing through it, is that a distortionless system can only have pure delay and that's it, and linear phase. So in the frequency domain, it looks like it's drawn out here. Constant, and then the phase is linear over frequency. So the phase is dropping down with a negative slope, because that negative slope comes about because of the time delay. We would never have a positive slope, right? Because that would say that the system is predicting time, like it's advancing time into the future. So we can't do that. So it's always going to have that negative slope to it. So that's distortion, and the two classes of distortion are amplitude, where it's not constant over a frequency band, and then phase, where it's not linear over a frequency band. And remember, group delay shows us that because it's taking the derivative of the phase response. So where the derivative is not constant, because a constant slope has a derivative that's a constant, whatever the slope is, or a linear phase, I mean, has a constant slope. So that, if we deviate from that, then we have a distortion system. And I don't mean just the non-linear type distortion like you looked at in the homework problem. So this is telling you, giving you 3 examples and trying to identify the types of distortion. And this will probably be in the mock quiz, because this is the next quiz up in my stack of quizzes. So it's one that's kind of based on this problem. So even though you're not having to do a real quiz on Thursday, it could show up on the exam that way. So let's just kind of take a look at it. The idea of the distortionless applies to the band of interest, and that's one of the things that I always have to make sure to keep in my head. When you're designing comm systems where you need to use filters, because that's the only way we can separate one signal from another. We have a signal we want, we have a filter to pass that signal, the filter blocks the signals we don't want to deal with. So right away you'd say that filter has amplitude distortion. In the bigger picture it does, because it will pass the signal and then not pass the signal in another region. So obviously it's got gain discrimination. It's got gain of unity in a passband and a gain of minus 80 dB or something like that in the stop band. But what we care about is in the passband. So in this particular example, the green shaded region is the first passband that's considered. So from minus to plus 10 hertz in this simple example, that's considered to be the initial band of interest. And if you look at the amplitude response, you see it's constant. Look at the phase, the second plot there, the one to the right, it's linear, so it's distortionless. So that's why this is highlighted, or this is noted. As long as we're less than 10 hertz, we're distortionless. But if we want to extend the band to, say, run from minus 20 to plus 20, then amplitude is no longer constant over that band, right? It just jumps between 2 values. And phase is also no longer linear, because the phase stops being linear and just hangs out at a constant value when we get below minus 15 or above plus 15. So in that regard, it'd be distortionless. So the way the question could be worded is, what band of frequencies is there no amplitude distortion? What band of frequencies is there no phase distortion? And then the second 2 plots there are just the group delay, which is a derivative of the phase, and the phase delay, which is just dividing the phase response by omega, whatever it is up here. I'm not really fond of using that definition because it's not as useful. See, it's in here somewhere. TP, you're just dividing the phase by 2 pi f, and that's called phase delay. But that only makes sense for a single frequency, and I don't really find that to be all that useful, because group delay is the most important one, because what do we send with one frequency? What sort of information can we send with one frequency? We can't do very much. We could signal with a tone, but if we're modulating that tone, in other words, switching it on and off, then that's going to spread the spectrum out, and it's no longer going to be a single frequency. Does that make sense? I mean, what type of signaling do we do that is a steady tone? There's no such thing as that, but a fairly steady tone is when we press a touch tone button down in the phone. That produces 2 tones, right? And for the duration of that button press, it is a steady tone. It's in 2 different frequencies, though. So even then, that would be sensitive to group delay because it's at 2 different frequencies. So group delay is the only thing I'm really interested in. I'm not going to ask you questions about phase delay because I find it confusing to have to talk about that, and I don't really make a big deal about it. It's just in here because it was in the book. So So those are the types of questions you can ask from that. So the last point in here is, what about the interval 10 to 15? Well, from 10 to 15, we actually have a small little piece of linear phase and constant amplitude, because that's this interval right in here. So in that interval, the gain is constant and the phase is linear, but it's not centered on anything. It's not centered on zero, it's centered on a carrier frequency. But that still qualifies according to the rigors of the definition. It's constant in the band and phase is linear. Went through nonlinear distortion already, and you had the problem on that. We'll bounce back into nonlinearities a little bit in chapter 3, because that's a way of looking at mixers. We're actually going to be looking at how the mixer works, and in lab, you two are in lab, right? That's one of the more interesting labs, because you face the reality. How do we build a multiplier at high frequencies? We build it with some sort of nonlinearity, and the double bounce mixer is a pretty controllable structure, but the simplest mixers were built with vacuum tubes and diodes ages ago, and there they were just counting on the fact that there would be some square law component, and the big thing that we'll see later will be if you have a device that has a squaring component in it. It looks like my pen's starting to have an issue. So if you have two cosines in there and you square it, you get the square of the first term, you get the square of the second term. Those are second harmonics, right? But the thing that we get out of there that's really important is the cross term. So we're going to get, from the squaring action, we're going to get cosine times cosine, and that then is a poor man's version of an ideal multiplier, where you'd have the omega 1 term gets to multiply times the cosine of the omega 2 term, and you get to form the sum and the difference. And you see that action in the double balanced mixer. That's the term that's generally the most interest, the sum and the difference frequency. Learn to suppress the other terms, and the double balanced mixer tends to do that, because the strongest components are going to be, well, DC doesn't get past depending upon which port you're using on the mixer, and the balancing action tends to get rid of the frequencies that go in, omega 1 and omega 2. So it's just kind of a way of making that work. In a DSP implementation, yeah, then you can just do straight multiplication in software. I don't know, does anybody have any question on that for right now? I mean, it's going to get looked at more in the next chapter, but it's something that the way time marches on, I think it becomes harder to convince people that this really is a challenge, because we're so computerized. We just think we can just do that in software. But how do you build a circuit to do that? That's the question, and that was the question from ages ago. So devices that are operating in the nonlinear region is what the answer was. And then another little twist in here is what happens if we're looking at this for a signal that has a continuous spectra. Then we just go back to the multiplication theorem for the Fourier domain and say if we multiply two signals in the time domain, we can involve them in the frequency domain. So that's, this example here was just, suppose the spectrum was rectangle, and then when we look at it through the square law device, we get the linear term, which is the original spectrum, and then we get the original spectrum convolved with itself. So we're going to get the superposition of the rectangle and then the triangle, and then you get this cute looking house. Does that look cute or not?
Well, let's not go too far.
Yeah. These things happen though, and these are things that show up in other more advanced topics with random signals and something called self-noise and things of that sort. Okay, now moving on. Ideal filters are what we're going to use in chapter 3 and 4 pretty much exclusively just to model ideas and get our feet on the ground with a concept. Is it going to work? Is it not going to work? So use the ideal filter. Like the ideal low-pass filter is this definition. We generally think of it in the baseband form. We're thinking of it just runs from 0 to B hertz, but because of our math modeling, it does have the negative frequency image sitting over there because it's a real impulse response, so it's going to have a symmetric spectrum. And while we're at it, as long as we're creating an ideal filter, we can make it even have linear phase if we want to, or a time delay. We can throw that into the model because that doesn't hurt anything. And we know we can't build it anyway, but we can at least have that built into our model. We can put in a time delay, and that can be useful for other purposes too. And then 1 minus the low pass is going to be the ideal high pass. And then we can use the modulation theorem effectively to take and form a bandpass response. So it's 2 low-pass responses shifted up and shifted down. And that would be the ideal bandpass filter. And it involves then a sinc function if it's a rectangle, but it's got a frequency component associated with that, the e to the minus j 2 pi f naught t naught. Actually, I didn't mean to say that. It's this term right here. So it looks like the time delay is on there to represent some relative form of realizability, and then multiply it times the cosine, and that shifts it up in frequency. And that technique can be useful in software. Reminds me of one of the homework problems from modern DSP, which, Chris, you might remember that one problem in chapter 5 that goes through, tell me what this filter is. It uses DSP blocks and multipliers, and you could build.
Yeah, no, I vaguely remember that.
Yeah, I like that problem a lot because it makes you think outside the box a little bit with how you can synthesize. And with software-defined radio and complex baseband signal processing, it's all real. I mean, you can do all those things. If you do need to take a design further and you want to see what some of the implications are of not having perfect filters, and this is what you're going to do in the first project, you will actually be designing realizable filters, and then you'll be sending test vectors through. So we have things like Butterworth, Chebyshev, and Bessel as prototypes for analog filters. If we want to actually build the simulation on the computer, though, we actually have purely digital filter types that we could take advantage of, like FIR filters, finite impulse response. They could be equal ripple. They could be windowed FIR, and so on, some of the other types of digital filters. But the book focuses mostly on analog prototypes because everything in the book focuses mostly on continuous time, but implementations nowadays vary from mostly software design, and then certain building blocks at the interface points are in analog. So you're expected to be familiar with both. So here is a Butterworth and the Butterworth polynomial and the locations of the roots for the Butterworth. What I have committed to memory, and you may see in a homework problem or may see on an exam problem, is this is the form of the nth order Butterworth. And you can scale the cutoff frequency away from 3 dB if you want to, but by default, when f equals fc, then you're at the 3 dB point. because then you've got 1 over 1 plus 1 plus 1 to the 2n, which is just 1, so you get 1 over square root of 2, and that's down 3 dB, right? And the poles are spaced uniformly on a circle of radius, the cutoff frequency in radians per second, in the left half plane of the S-plane. I guess I should say it at least once. The Butterworth is also known as the maximally flat, and the reason why it's known as maximally flat is because the number of derivatives that are equal to 0, like right here, and then if you carry all of this all the way out to infinity, so you look at the Butterworth filter, and at 0 and at infinity, it is so flat that you can take up to n derivatives and they're still equal to 0. So that maybe doesn't hit anybody, but the way I like to think of it is think of your kitchen counter at home and think of having a ball bearing, and if the surface is so flat that it's higher order derivatives of the surface are 0, that means you place anything on that surface and the ball bearing is not going to start to roll in any direction because it's just that flat. I don't know if that means anything, but that's, you know, how flat is maximally flat. It's the maximum, you know, the derivatives, all the derivatives are equal to 0. And I'm not a contractor, so I don't think contractors build surfaces where they insist upon derivatives being equal to 0, because they probably don't even think about what is a derivative at all. They just build things with their hands. Chebyshev allows ripple in the pass band or ripple in the stop band, depending upon the type of design. The one that's mentioned here is the ripple in the pass band, and that was the one that you built using Python, right? That had ripple in the pass band, and then it asymptotically went down to the stop band. And the phase of it is nasty, just like the Butterworth is nasty. The group delay is far from flat, and you should have gotten a nice non-constant group delay that peaks up pretty much at the cutoff frequencies. Its poles lie on an ellipse, which is controlled by the ripple. Bessel is linear phase as best as possible. It's not perfect, but it's very flat. So here's roll-off comparison with a 0.1 dB ripple Chebyshev and then a Bessel and a Butterworth. In general, the Chebyshev is more popular because it does roll off a little bit faster than the Butterworth for this particular design. And then I pasted this in from another document. This is just the group delay comparison for a particular design. And this is showing that the Bessel is very flat. Butterworth peaks. Chebyshev peaks a little bit more. But as Dr. Zimmer would always remind me, if you had a really small epsilon dB value for your Chebyshev filter, it can actually do better than the Butterworth filter can for group delay. And he would always say if you go with 0.1 dB or something, you will do better than the Butterworth or something like that. I don't remember what the exact example was. And the roll-off rate would be slightly better, so he would always advocate for a Chebyshev filter. The different types of filters that are out there are LC passive, which is what I passed around in the board I did for the lab. RC op-amp filters are popular at lower audio frequencies, and if you use a really wideband op-amp, you can use them for RF. There's quartz crystal filters, there's ceramic filters. Ceramic filters are on the radio board that's used in Lab 4. They're pretty good. Surface acoustic wave filters are good in the range there and above 1 gigahertz now too. They're very popular. And it's in this area that I had my document, but my computer rebooted itself last night and I didn't go looking for the article that I had saved out from electronic design, so I don't have it, but Qualcomm is a big manufacturer of cell phone components, chips, and they even make microwave RF parts. So they have a newer surface acoustic wave filter that's good around 800 megahertz and up to the cellular band, which is around 1200 megahertz or 1.3. That has, I guess, a 1 dB less insertion loss than what an earlier design had. So Qualcomm is pushing this for 5G, and they're selling a lot of filters right now. And this article just said that they kind of have a monopoly on some of the ideal filter designs for handsets. So every new cell phone will have to have a Qualcomm filter, perhaps. Broadcom is another company that makes chipsets. Has everybody heard of Broadcom before? They're pervasive too, and they have their own version of something, but if somebody like Qualcomm or Broadcom, and Qorvo is another company that makes bulk acoustic wave filters, or BAW filters that are used in cell phones. If somebody comes up with a really good filter design, good loss, and they can get their filter in every handset that's sold, that's a lot of money right there, because the volumes are phenomenal. So this was in the news last week, and apparently Qualcomm is always under the eye of the US, but in this case it was under the eye of somebody in the European community, saying that they have a stronghold on the market and they're not happy with that. You know, everybody gets upset. We're in a capitalistic system in the US and most of Europe, you know, Western Europe, but still, if somebody holds a lock on the market, people start crying, monopoly, monopoly, we can't let this happen. You guys have any comments? One of our presidential candidates has got me worried because he's talking about bringing back unions. Everybody's going to be in a union again, and unions and also monopolies are kind of, all that stuff has drifted through time before. It's just, I like not being in a union. I could be at a university probably somewhere in the country where I'd have to have joined a union and then pay my union dues because they're going to negotiate for me.
Yeah, no, I'll fight that. Union's terrible.
But unions is to protect workers. Monopolies have to be stopped to protect consumers from practices that can make you spend more money. But it's a hard one. So I went through some examples in Python, and you did that already, and that worked for you, I believe. The last topic in here was pulse resolution, rise time, and bandwidth. So I did assign you a homework problem on this. It's not a really biggie problem, but in the end, what this theorem, or Lil's development, is, it says that if you have a pulse and you define the bandwidth of the pulse to be so that you have equal areas between the rectangle, which is what sets W, in the area of the spectrum of the pulse shape, and then you take the time domain version of the pulse and do the same thing and call the half width T/2, you can show from the above formula that W is always going to be greater than or equal to 1 over 2t. So if you were to take that right down to the wire, you would say W is equal to 1 over 2t. So the bandwidth that it takes to support a pulse of width t is is 1 over 2t, is what it's saying. It turns out to not be a real accurate formula. It's an upper bound, so it's not necessarily tight. But the problem that I gave you involved the Gaussian pulse. Remember, Gaussian, Fourier transform of Gaussian is another Gaussian. And for that particular pulse shape, it's exact. The bound is exact, and that's what that homework problem established, that if you went through that and followed the steps here, you would find that that's exact, and that's in that solution that's now posted. But here, the rectangle pulse is used as an example. So there's the rectangle pulse. Its t over 2 value in this case was normalized to be 0.5. And when you do that for the Fourier transform, you're doing it for the magnitude of the sinc function. And you have to establish that the lower bound is going to be that W value that I've got the arrowhead pointed to. And I think, no, I guess I thought I had this worked out to show you that, well, in this case, W is clearly greater than 1 over the 1 over 2t formula. So it doesn't work very well for the rectangle pulse. Rise time, you've studied rise time in electronics, right?
Mm-hmm.
So there's a question on that in the first homework problem too, finding the rise time for the step response of the Butterworth filter. I think that's right. Just make sure I have that right so I'm not saying what's not true. Given the step response for a second order Butterworth filter, they give it to you all worked out. Find the 10% to 90% rise time in terms of F3. So what you get to do is plot that, and then you can analyze it and find out how it's proportional to F3 by just doing some normalizing. And I'll probably give you some hints on it, but 65 is kind of an interesting problem. Because you also, this part B is the group delay response where you have to take the derivatives. So now we're done. Sampling theory we'll use when we need it in chapter 3. Hilbert transform we'll come back and use a little ways down the pathway in chapter 3. Any fanfare for having finished the chapter? The review seems like it takes a very long time, but I've always thought, and I've done this for too many years, that it could go faster, but then every time I get into it, I realize it just can't go faster because your brains have to ramp back up on it. We have to introduce some new material. We have to establish everything just kind of works against you to make it happen too fast.
Only took 6 weeks.
And it's pretty embarrassing because the semester is only,
16.
yeah,
16?
yeah.
15 with finals?
So I don't want to think about it.
Yeah.
It just happened though.
Our midterms about
So I'm ready to get started on this chapter. And then we'll jump over and look at the notebook. The notebook for chapter 3, which I've got loaded right now and is on the website, has got some cool demos in it. I'm going to have a lot of audio demos in here that let you hear things as well as see things in plots. So now we're into this part. We've already studied this already, but we're looking at a modulated carrier, and we're, for the time being, going to not do any modulation into the phase, but we're going to focus on having the modulation all be applied, or the message all be applied to A of t.
question.
Yeah,
Do you think by the end of today we'd be able to go over at least double-sided modulation?
Yeah, that's what we're doing right now.
and AM modulation?
Yeah, that's what we're headed for right now.
Okay, cool.
But keep me posted on if you're thinking I've got it good enough. So the first modulation is letting A of t be linear modulation being proportional in some way to a message signal. And the very first one is double sideband. So double sideband is A of t is in fact directly proportional to M of t. So here it is. It's just sitting right in there. We're going to take the carrier cosine 2 pi fct and multiply it by a message signal. AC is just a scaling factor, and the message is speech, music, digital, pulse, waveform, whatever. It can be anything. So getting the spectrum for double sideband is just simply Fourier transforming both sides, and we've been through the modulation theorem already. So we just upshift and downshift the spectrum of M of t, which is M of f. And if we're looking at it in the time domain, we have a message signal the way I drew it out here, and then we apply a carrier to it. What happens is the envelope is controlled by the message, and the envelope gets drawn as I did there on the left, but then it gets flipped over because the carrier is going to make the sign of the envelope effectively take on either positive or negative. So the way I have it drawn there on the right, I'm just showing it as a positive and a negative envelope, and then it's filled in with carrier because the high frequency carrier is in there. And if you've already started on the lab, which you did, you've seen this, right?
Yep. I've done this. I've done it before. I just figured it'd be good to make sure.
Yeah, no, we're going over it. I'm going to jump over to Python when I get done here. And so if we then move on and say, okay, suppose the spectrum is a triangle of the message. Now, M of t up there and M of f are not a Fourier transform pair. I'm now just shifting gears. I just sketched out a waveform, and now I just sketched out the spectrum of some other waveform. What would the waveform have to be if it's going to have a triangular shaped spectrum? Sinc squared, right? And that's not even a causal signal, so it's a little bit convenient to just do that. But at any rate, multiply times the carrier, modulation theorem shifts it up and down. So when we shift it up and down, then we get some other terminology that goes along with it. We think of the spectrum of the baseband or M of t signal as having an upper sideband and a lower sideband. And we really don't think of that when it's at baseband. We just say it's symmetrical. But when we're thinking of communications theory, we're actually going to think that we have the upper sideband, what sits above the carrier, and the lower sideband, which sits below the carrier. And then, of course, the mirror image is over there at the negative carrier frequency. The reason why the upper and lower sideband is talked about is we'll find out when we look at demodulation, coherent demodulation, which is next up here, that when we study single sideband modulation, we find out that we don't have to transmit both upper sideband and lower sideband. We can transmit one or the other, and we're perfectly okay. And this was discovered, long time ago, and the telephone company really homed in on this and said, okay, when we send voice channels from one end of the country to the other using microwave relay towers, which is what they did at one time, we can pack twice as many voice channels into the same band of frequencies if we just do it upper sideband or lower sideband. Amateur radio people have long used single sideband modulation, and ship to ship and ship to shore international radio systems still use single sideband. It is not that popular anymore, but I do have the first project set up to have you play with it, just because it's kind of a nice learning experience. But we're not at the single sideband yet, but I'm just pointing that out to you, that that's a terminology, the upper sideband and the lower sideband. So how do we demodulate? And the first several of the homework problems kind of spin around on this idea. It's deceptively simple but it is what it is. A coherent demodulation scheme is what it takes to get back the message for double sideband. So the transmitter's sitting there on the left. We have a channel in the middle, which has, in the simple way of thinking here, just a propagation delay in going from here to here. So we have some sort of delay, but we're not going to model that right now. Some time delay for propagating through space. And then there could be some attenuation, but we're not modeling multipath or anything like that. We're just assuming that signal cleanly gets to the receive side, and at most it has a pure delay, but it doesn't have any attenuation. As a function of frequency, it has just a constant. So now we have the received signal. So what the modeling now does is, okay, the coherent demodulator is composed of two blocks, a multiplier and then a low-pass filter. And you'll be sketching this out in the homework. You'll be drawing the block diagram for the receiver, and there's a whole two components to this. Yeah.
We'd be attempting what we did in circuits 2, where, because the final project was you had a signal, you modulated it, it went through a channel where it had some kind of like corruption variable, or like let's say it was Gaussian white noise or something, and then you would demodulate it, it would just sound terrible, so you'd have to figure out ways to mitigate channel, what's it called? It's the
Channel
word.
distortion.
Distortion. Yeah.
Okay.
Are we doing
I don't know what you did there. What class was that in?
Circuits 2.
Okay. Dr. Trimboli's stuff?
No, it was semi-art, but it was using Trimboli's.
Notes?
Yeah.
Okay. We are going to be looking at that, yeah.
Okay.
But we're not going to look at it probably in the exact same way, and we can't look at it fully unless we have random processes.
Yeah,
But we are
just
going to
using
do
MATLAB.
things. Pardon me?
We were just using MATLAB to emulate the effect.
Yeah. We are going to talk a little bit more about it, and of course you'll be using Python here, and that's right, naturally. But the fact is I can do the audio right in the Jupyter Notebook, and I can even do the real-time audio signal processing right in the notebook.
Do audio?
Yep.
Huh.
I have a package called Pi Audio Helper, which appends onto Pi Audio,
It's
and
the hardest thing you'll ever do in Jupyter.
Really?
but it works great. I
And
mean,
yeah, once you get it working, and
Yeah.
just getting it to work.
come to my office sometime, and I'll put some headphones on you. I've got something pretty cool with 3D audio. I can spin audio around your head and move it around your head and give you a test to see if your cognition for your binaural sensing, and that's what it's called, binaural, because it's two sensors, if your brain is trained properly. And I don't have your head model, but I have a mannequin's head model in the system. I've got a PhD student working on other solutions to that with deep neural networks, and then we have another solution with COMSOL and 3D head models through photogrammetry. But at any rate, your brain is trained, so even if I use a model that's fairly close and I can synthesize in real time the sound moving, you can sense, is it going up, is it going down, is it in front, is it in back here? And I've got that in my Bose headphones, and then
It's the thing they do for a lot of home theater these days. Like that's a big selling point.
What, 3D audio?
Yeah, being able to bounce audio correctly in a room.
Yeah. Well, this doesn't bounce it. This is only one path, but it works as if you were in free space and the sound was coming from there. How would you perceive it? Or from there, do you perceive it correctly? And it's kind of cool. And then I put it into motion. And for me, it makes me feel like I'm in an amusement park ride a little bit. I start to get a little bit seasick feeling if I spin it fast enough, make the music play and have it just spin around your head. And then I have parameters to control it. So I've had fun with that, and took that to the SciPy conference last year and tested a bunch of human subjects without having approval because people just wanted to try it out. So I learned some things from that. But my student is working on doing human subject testing. Okay, so getting back to this, suppose we make the message signal a sinusoid. Well, let's just not do that yet. I got sidetracked there. Let's just go through the block diagram. So this is what communications engineers do a lot. If you were given this block diagram, you would say, does the receiver work? I know I can generate the transmitted signal. What I want to do is prove to myself with my ability to manage the math and the time domain and the frequency domain, is this block diagram going to get my message signal back? So the question is, are we getting back our message? And whenever I say message, you can think old-fashioned, voice, sports, basketball, country western music, rock music, talk radio. You can think all those things, but it could be digital. It could be pulse amplitude modulation, pulse code modulation, which we'll be looking at later. So it's just a generic term. It's some type of waveform that contains direct analog info, or it could be digitized something or another. So we'll have both of those contexts. So assume the channel is ideal. There's no noise, there's no multipath, so we just have a direct connection. So we plug in the received signal, which is what's sitting right here. That's what was sent, and we're receiving it without attenuation, without any additive noise. And then the 2 cosine is just that. So what do you do when you get to a new setup? You do the math. So in this case, just multiply using the trig identities, and in this case I'm using this trig identity to break it down into those 2 parts. If you don't like that trig identity, which one do you like? I'll tell you which one I like the most, one that you use the most in this class. You're going to use a lot of other trig identities at various times, but the one that I use the most is just this one. What is that? So it's 1/2 it's that. And of course cosine is an even function, so if you don't like θ1 minus θ2, what can you do? Flip it, right? You can just say θ2 minus θ1. No differences. And then if you need to do sine times cosine or sine times sine, you can look up the other ones. But this one, I don't have the other ones totally committed to memory. I mean, I can get them back in. This one I have always ready, and this is probably the most important one. And from this one you can do the cosine squared, because if you have θ1 equals θ2, then you can use this to prove that, right?
Yes. It's a bit easier for like sinusoidal waves, such as like audio, but for like videos, such as like your like football or something, and it's the PN data transfer, so it's a bunch of high rises and low rises on a clock.
Okay.
And wouldn't that be a lot harder to modulate, because it has a bunch of, in the frequency domain, like doing a square wave-ish, has a bunch of leaping harmonics? And when you filter
not
them, you delete them?
You could filter things that you need to delete, but we have the modulation theorem, so we can handle that in the frequency domain, and then we can see what's going on, and then we can say, okay, yeah, maybe some of the components I can delete, so I'll filter some of those out. But we can cope with it.
You can handle a little bit of signal degradation for the modulation.
We can handle pretty much anything we need to handle. And if the analysis gets too hairy, too much for you, you simplify it down and get a handle on it with some simple models like this. And then if you need to go and explore further, you build up a higher fidelity model in Python or MATLAB, and then you just give it a test. there. So, and I'm going to be doing that for some different waveform types in the Jupyter Notebook. Mostly things that you can listen to, just so you can get a better feel for it. At any rate, we're going to run out of time. I won't get into AM too much if I don't keep moving. So we're going to do the multiplication. We have the two terms. And this term right here, that's the term you want, because that d of t is right here. That has got pretty much got the answer in it that we want. That's the portion of d of t that we want. The other term we don't want. And the fact that the other term is there for the case of the waveform that I presented earlier, this is what d of t looks like. Notice the difference between this guy right here. That's got the envelope symmetrical top and bottom. As soon as we multiply it by the coherent carrier, it gets flat across the baseline. Notice the difference? It's pulled in like that. And that's because of the double frequency term and then the fact that it's combining with the AM of t. So this is looking closer to what we started with, but we still have it filled with carrier. So what we're looking at spectrally is we look at what those two waveforms are. The center term, the A C times M of F, that's what we want to get back. And then we have our second term right in here. That is the term that's got the message signal shifted up in frequency by 2fc and down by minus 2fc. That's the one that we want to get rid of. So we get rid of that one simply by low-pass filtering, and then that removes the double frequency term. And you'll see that in the lab experiment. To me, it's very cool because it's like, of course, I just need to filter it away. But the problem is we have to build a perfect filter if we really want to get rid of everything. But the thing is that in general, there's a cut in here. So W is generally much less than 2fc. So getting a filter that can get rid of the double frequency term is generally not that hard. The AC factor, that can be dealt with downstream with an automatic gain control or some gain regulating device to keep the signal gain constant. And then, like I say here in the bullets, we just make sure that the cutoff frequency is greater than W and less than 2fc minus W, so we can get rid of it. So now the next thing I'm going to do is I'm going to say, okay, we don't have a perfectly coherent carrier. Let's suppose that the C of t, which was this piece right up here, so now we're going to take the block diagram, we're going to modify it. We're going to suppose that we don't have a signal in the demodulator that is exact what was sent at the transmitter, or takes into account the Doppler shift between the transmit and receive signal. Understand Doppler shift is an issue here. We know it's part of the way satellites function. They have small to large amounts of Doppler depending upon how much relative motion the satellite has relative to our origin. Geostationary satellites are what? How much Doppler do they have? I mean, I don't mean absolute number, but in theory, when you think of a geostationary satellite, you think you could point your finger, and as the day goes by, that satellite is always in that same location up there, right? It has a small sinusoidal fluctuation that goes on with it. But a GPS satellite moves by, and it has a fair amount of Doppler. Then you take a low Earth orbit satellite, it moves by very quickly, and it has an even higher amount of Doppler. You also put yourself in your car with your cell phone and drive like crazy to Denver because there's no traffic, so you drive fast. You create a lot of Doppler, and the cell tower knows that, you know that, but yet you can still communicate. So It's been managed, and it's not by accident. It actually works. FM radio can manage it too, and it's just voice and it's legacy. So some certain analog schemes, AM radio, FM radio, they're kind of immune to Doppler because they're not that sensitive in the demodulators that you notice it. Digital modulation is very sensitive to it, so you have to take care of it. So nowadays, we have to manage the Doppler for any digital transmissions. But anyway, let's just suppose, to get an idea of how sensitive things are in this receiver, let's suppose C of t is not a perfect copy of what was sent at the transmitter. So there'll be this time-varying phase thrown in there. And with that time-varying phase, it could just be 90 degrees. It could be a small frequency. That could be 2 pi times delta f. So this could be pi delta ft, so it's a small linear phase. So we plug that into our math, and now we write out d of t again, and then we assume, this is still approximately at twice the carrier. So low-pass filter removes this. But now we're left with this, assuming that this has been managed. Just pretend that we have it managed with a gain scaler. So we see m of t there, but we say, there's cosine of theta of t in there. If it's slowly varying, that would be like a time-varying attenuation. The volume would come up, it would go down, it would flip the signal over. If it was voice or music, we probably wouldn't notice it too much. But if it was data bits, what's going to happen if we have the sign, cosine of theta changes in sign? That's going to take the data bits and flip them upside down. Is our system going to be able to cope with that? Unless we handle it a priori, no. It's going to be bad news. So, and then if we do model as a small frequency offset, we can look at it as sort of a worst case scenario, which I want to demo for you before we leave today, if at all possible. Suppose theta of t is, should have had a 2 pi in here. So you have a 2 pi delta ft, and what will happen then if we're receiving a tone at a frequency FM, we're going to end up multiplying the message by that cosine of 2 pi delta fm, or 2 pi delta ft, and that, again, from the trig identity, is going to give us 2 different tones, right? One shifted up, one shifted down. So we end up hearing 2 tones, and it sounds pretty awful. I'd like to demo that if time will permit, but I am going to suspend going over to Python right now and go look at AM for a moment. We can come up with a means to get the carrier back at the receiver, and this is where phase lock loops come in. A way of doing that would be a tracking filter. We could square the signal at the receiver. We could then bandpass filter it at the double frequency. And after we square it, we removed, made the power in the message positive, or we made the envelope of the signal positive for all time. And then we could filter that and lock a phase lock loop up to it to get a reference signal that's phase coherent with the transmitter. Or another technique would be simply to send a small unmodulated carrier along with the double sideband signal so that we can always get access to the carrier at the receiver. This picture right here is the first idea, though, of squaring it and getting something at double the frequency and then dividing it by 2 to get back to the carrier that we need so we can coherently demodulate it. So this is still, this right here is still the D mod. And this part in here is carrier recovery. the phase lock loops class that I teach on Wednesday mornings is exactly on the topics related as how to get a coherent carrier back again for different types of communications links. And it ends up being vital, and phase lock loops are pretty popular, but there's other means that can be used too. So double sideband is sometimes also called suppressed carrier, because when we send the native double sideband, there's no pure carrier in the signal, and we need it. So another technique is to actually add a little bit of pure carrier at the transmitter so that we're transmitting some pure carrier along with our double sideband spectrum, and then we can use that to help get the carrier back again, the pilot type carrier. And I'm actually working on a project problem right now for the phase lock loops class where they're going to experiment with this only for phase modulation, not amplitude modulation. Sound interesting? Maybe not. Not interesting.
I like magnitude. Phase is gross.
Well, but there's advantages to phase, and I'll get into that later. I won't try to explain it right now, but amplitude is very susceptible to things, and I'll explain that more later. So what is amplitude modulation? To solve the problem of the double sideband modulation, they just said a long time ago, let's just send a large bias A along with our message, and we'll adjust the bias, and I'm just going to jump ahead because we're going to run out of time here. We'll just jump ahead so that the envelope is opened rather than being closed, so it was interleaved like my fingers were coming together. It's now pulled apart. And what we can do in the envelope, when we add this bias term in, we can come along with an envelope detector, and we can pretty much just say a diode detector can just say take the positive half of the waveform, and then we can low pass filter it, and notice the envelope is writing there on the top, and that's our message that we started with. So we can pull it away very easily, and that's this circuit right here. Just pulls that back, and then the RC filter removes the carrier, and we've got it back. So this is a nonlinear circuit with memory, so it's a little bit tricky to analyze, but the concept would be half-wave rectify and then filter to get rid of the double frequency term, or get rid of the carrier term, and that's the basics. And what makes this so powerful is that back in the early days of radio, the transmitter, the receivers for a coherent double sideband system, just out of reach. We could not build radios for people that they could afford. So a simple radio would have just this envelope detector in it, and that's all it took to receive an AM broadcast. So the transmitters were made extra powerful to send all that extra carrier just so that the envelope detector could recover the message. We'll go through efficiency calculations on Thursday that talk about how much power is put into the pure carrier and how AM is so inefficient, but it makes the burden go from the receiver to the transmitter. So that's what we do in AM radio to this day. We don't use the coherent. The coherent, though, is used in deep space when we want to send a weak digital message back from a Explorer satellite way out there in space, and we want to use just the bare minimum power to send the information, not a synchronization carrier, and then we build a sophisticated phase lock loop tracking system at the receiver and can get the data back again. And that makes sense, I think, doesn't it? We don't want to put a lot of power into the carrier if we don't have to. We want it in the message. So that's been the name of the game in satellite communications ever since the early 60s when it came into being. I know I'm out of time. I'm just going to show you where it is in the notebook, though. In chapter 3 here, and what the name of the game will be. Same old start to the notebook, but we have test vectors in here which you'll be playing with when you do the first project. I've got a female US, a male US, and a male British test vectors. So I've loaded them in. They're at 8 kilosamples per second. I've just taken the vector and I've added some noise to it, and then I can just play it back right here in the notebook.
Hoist the load to your left shoulder. Take the winding path to reach the lake.
I want to get the audio working here someday, so What I got to do is figure out if I can get it to work on through my other audio device.
Stray cat gave birth to Pixie. The young girl gave no clear response. The meal was cooked before the bell rang.
Where are the speakers on here? I don't see the speaker icon. There it is. That. So let me try it again.
Take the winding path to reach the lake.
I just wanted to prove I can do this when I want to do demos next time. So that's a little bit nicer, right? I'll probably annoy you next time by playing certain things. When you hear tones,
No, never.
it'll be
It can
annoying.
never happen.
Traverse the valley plains and home the lake.
So this is some fun things we get to do later. But this notebook is full of that type of, those types of things in it. So we'll work double sideband with digital and analog waveform speech with tones, and I've got a number of different things to go play with in here. And then once we do that, we'll do AM modulation, and then single sideband, then some of the other things that go on, frequency translation and mixing. This is set up kind of like the last one. So tomorrow in lab, let me know. Maybe I'll stop by before I head out of here. I'm trying to remember what else do I have to do tomorrow before when I'm doing my other class in the morning. But hopefully you're set. Do you feel reasonably okay?
Yeah.
Not
We
sure.
got through, I mean, we still have two more weeks.
Okay.
So, for that, this is a 3 week. But you made it through problem 3 out of 5.
I made what?
You've talked about everything up through problem 1 through 3. There's still 2 more problems on the lab.
Okay.
Just keep
I'll,
going,
I'll keep going. I won't stop.
because you stopped where I stopped with that. I finished the amp modulation.
Okay. I don't think I have you do anything with the